Hello everyone! Up to this point, we considered systems with positive exchange integral. As this takes place, the energy of the system is minimal if the magnetic moments have the same direction. And what would happen if the exchange integral is less than zero? Let us try to study this question in detail. There are too many mathematical manipulations in this lesson, so I recommend to perform these manipulations independently for better understanding.
Again, denote that Jij as j, which is less than 0 for the nearest neighbors, and Jij is equal to 0 for other magnetic moments. The beginning Hamiltonian will have the same form. Considering the mean field approximation, rewrite it in the following way. Further, we shall leave out E0 constant, because it should be taken into account for energy calculation, but it is unimportant for order parameter obtaining. Finally, receive the following Hamiltonian. This Hamiltonian has the same form as the Hamiltonian within the Ising model for ferromagnets. Earlier, we denoted the mean value of operator sigma jz as x. X is the order parameter. For every j, these mean values sigma jz are identical due to the fact that in ferromagnetic alignment all magnetic moments have the same direction. For antiferromagnets, it will be different. For two neighboring magnetic moments, energy is equal to minus j sigma iz sigma jz, and it has the minimal value if the product of sigma iz and sigma jz is equal to minus 1, i.e. sigma iz and sigma jz have different signs. In other words, neighboring magnetic moments have opposite directions. This applies for any pair of neighboring magnetic moments. What are our expectations? For one-dimensional case, it will be like this. For a two-dimensional simple cubic lattice, the ordering is shown on the picture. So, some atoms have positive mean value of operator sigma iz, and other atoms have negative mean value of operator sigma iz. Thus, we cannot consider mean value of operator sigma iz as x, which is constant for any I. Let us divide our system, the whole lattice, to two sublattices A and B, with alternating arrangement of the nodes. See the picture. Such sublattices are called embedded sublattices. Since we consider that exchange integral is not equal to 0 only for the neighboring magnetic moments, such division on two sublattices suggests that magnetic moments of one sublattice do not interact with each other. Let us write the Hamiltonian considering the division on embedded sublattices. If the ith magnetic moment refers to a sublattice, we shall denote it as IA. Analogously, if the ith magnetic moment refers to B sublattice, we shall denote it as IB. We shall write the operators sigma IA and sigma IB for projection operators of these magnetic moments for A and B sublattices respectively. So the sum throughout the whole lattice consists of two sums for each sublattice. The Hamiltonian has the following form. Since we consider that only neighboring magnetic moments interact with each other, then the following equality takes place, where JIAJB is equal to J for neighboring magnetic moments, and Z is the number of the nearest neighbors. Here they denote the mean value of operator sigma JBZ as XB. It is the mean value of magnetic moment projection in B sublattice. We consider that the mean value of operator sigma jbz does not depend on the magnetic moment position in B sublattice, since all these moments are located in the same environment of magnetic moment from A sublattice. Analogously, we obtain the following equality, where the mean value of operator sigma jaz is equal to xa. It is the mean value of magnetic moment projection in A sublattice. Therefore, we have two different order parameters, XA for A sublattice and XB for B sublattice. Finally, for our Hamiltonian, we obtain the following form. Denote the effective magnetic fields acting on A and B sublattices respectively in the following way. Therefore, the Hamiltonian takes the following form. As in the case of ferromagnets, we obtain the Hamiltonian of non-interacting magnetic moments placed into the effective external field, distinct for each sublattice. Denote HA and HB Hamiltonians in the following way, and rewrite our total Hamiltonian in the following form. Since HA acts only on A sublattice and HB acts only on B sublattice, we can obtain the following system of equations for the order parameters. In the absence of magnetic field, this system can be simplified. One can see that XA and XB have the different signs. Since exchange integral is less than 0, let us show that a solution with XB is equal to minus XA exists. Denote XA as X and XB as minus X. Since exchange integral is less than 0, we obtain for X the following expression. Denoting product of z and absolute value of the exchange integral as Tn, we obtain the familiar equation for the order parameter. This equation has the same form as for a ferromagnet, but instead of Curie temperature theta, one can see another temperature Tn. The solution is already known. At temperature is equal to Tn, the phase transition takes place, and order parameter becomes non-zero. All formula that we obtained for ferromagnets are valid by replacing the Curie temperature theta on the Tn. The value Tn is called the Neél temperature, or transition temperature into antiferromagnetic state. Since XB is equal to minus X at T is equal to Tn, the spontaneous magnetization occurs in every sublattice, but atomic magnetic moments in these sublattices are oppositely directed. Total magnetic moments of A and B sublattices are equal in magnitude and opposite in direction. That is why the total magnetization is equal to 0, but the differential magnetic susceptibility may not equal to 0, in contrast to traditional one. As we have seen, the total magnetization in antiferromagnet is equal to 0. Therefore, the traditional magnetic susceptibility is equal to 0 as well, but the differential magnetic susceptibility may not equal to 0. Let us show this fact. Differential magnetic susceptibility of antiferromagnet has the following form. Considering the system of equations for order parameters and taking into account that Tn is equal to Zj, we obtain the following system of equations. Partial derivatives dxa by dh and dxb by dh take the following form. Making several mathematical manipulations and summing up the equations, we obtain the equation for partial derivative sum. We can express the sum of partial derivatives as follows. Finally, we obtain the differential magnetic susceptibility. Let us analyze this equation in more detail. In the absence of magnetic field, the expression for the order parameter takes the following form. In the case of t is greater than Tn, the order parameter is equal to 0. Therefore, we have the following expression for the differential magnetic susceptibility. In the case of t tends to Tn, the order parameter squared has the following form. Therefore, the expression for differential magnetic susceptibility looks like this. So, if t tends to Tn, differential magnetic susceptibility tends to Bohr-Magneton squared n by 2v. Let us show that if the temperature decreases below Tn, differential magnetic susceptibility decreases linearly. In the case of t is much less than Tn, the order parameter squared takes the following form, and thus differential magnetic susceptibility takes the following form. The resultant differential magnetic susceptibility characteristic dependence on temperature for antiferromagnets is shown on the picture. Note that in the case of antiferromagnetism, the temperature dependence of differential magnetic susceptibility does not have the divergence, as in the case of ferromagnetism. Okay, in this lesson we spoke about the phenomenon of antiferromagnetism. To describe this phenomenon, we introduce embedded sublattices and define the order parameter for each sublattice. We obtain that antiferromagnetic phase transition occurs at Neél temperature. At Neél temperature, spontaneous magnetization appears in each sublattice, but atomic magnetic moments of these sublattices have opposite directions. We found that in spite of the total magnetization of antiferromagnet is equal to 0 and traditional magnetic susceptibility is equal to 0, its differential magnetic susceptibility is not equal to 0. Moreover, in the case of antiferromagnetism, the temperature dependence of differential magnetic susceptibility does not have the divergence, as in the case of ferromagnetism.